We are live, waiting pipeline to complete, finish. So steps for this stream are going to be analyze the training script and paper reading. Okay. Let me share the stream. Let me just share the stream to our let me add Robert to the NLP study group. Okay, let's paste the newest stream here. Current stream just started. Nice. Let's add Robert to open NLLB project as well. Okay, guys. That's it. What does WB mean? I might be a noob. Boomer. What's WB? WB meaning. Welcome back. Thank you. Thank you. I didn't know what's the tilde. Okay. Guys, we are back. Filtering is still running because unfortunately I went to do a workout. I was running and it just stopped on the breakpoint here, so it was not running after it completed the 35 million file. So hopefully this one is going to be faster. Yeah, we'll have to just manually babysit it a bit more, but we're going to focus on training script and we're going to go through the paper as well. So let me open up Versec here. Let's go back to our train script and let's analyze it step by step. That's gonna be the goal here. Hello, you beauty. Hi, Brian. Welcome, man. Welcome, guys. Nice to see you here. How is the? I didn't have the time to see your struggles with the environment. Hopefully, you managed to solve all of the issues. I'm just thinking. Let's quickly skim. So ultimately, once we start running the training, we will be running this step by step. So that's going to be much more powerful. What I would love to do until then is figure out the roughly the code path that we'll be taking. So let's see that. We go here. Do we have module name here? Where is the module name specified? I guess in the base config. Let's see, let's go up here. Are we importing any configs? Dictionary config, omega config, training config, here it is. And you can see here module name. So that's gonna be the default one, right? This is gonna be the default value that we are basically overriding. So let's just open one of our YAML files side by side, split to the right, open the base config. Base config is, how do we know this is, how does the system know that we're picking train config as the base config? Okay, because we maybe say, let me think for a second, guys. Okay, here is the interruption from the, we are at 140. Almost halfway there, basically, with filtering. I'm trying to figure out why is the train config picked as the default one, if you know what I mean. So here are the this is the configuration file that we'll be using. I'm just wondering, why are we picking train config as the base config? Okay, because main config here is train config, and main config is used where? This is probably just some Hydra stuff. So let's just assume, oops, okay, again, let me just open this on the side so it's not interrupting us. Let me just open it up on the side. Give me a second. I'm gonna close down all of these files. Okay. Hit F5. Okay. Close all the files here. Close all. Looking good. Let's go. Train config. Here it is. Cluster config, dataset config, model type config. We kind of went through all of these already. Let's just see whether there is something else interesting. I really like their system, honestly. This Hydra system works very nicely, very neat. I haven't seen a better system, honestly, so far. SSL task, restore, fine tune. Okay. No special insights there, other than we'll be using sweep MMT as the module name. So if you take a look at here, we'll be going to the root of the fairsec and then running Python m and then calling that particular file and then passing a bunch of arguments. Arguments such as these, a ton of stuff for training, and then we basically submit that file. So let's open up quickly the sweep MMT. Sweep, no, where it is? Where is it? It's here, I think. Nope, it's not. It's under modeling sweep. Let's find it. Under modeling sweep. Okay, here it is. So this is the function that we'll be calling. And then this one, I have mosquitoes in my house. Oh my God. There's so much mosquitoes because it rained over the last couple of days. Post process. Hyperparameters. So we just call sweep main and we pass in this get grid. Let's see what the main function does. This code is somewhat slow for some reason. If this is glitching, what we can do is, well, first we can manually find the main function, which is not here apparently. So maybe it's somewhere here. No, it's not. Let's see. What's sweep? Sweep is import sweep and then call main. Okay, then main is probably here. Okay, here is main defined in the init file. And what we do here is we grab the arguments and then we call the backend main and we pass the get grid. Okay, so what's the definition of backend main if we don't hit this line. I'm not sure. But I think I recall when I was playing with this before that we need to go to the CLI this here and then find train. Okay guys, I make a suggestion here. Let's go and just cover the paper, because this is gonna be going like this through the code is not going to be as insightful. I don't know if you have any thoughts. Let me see, Hydra train. I'm not sure whether we are gonna run Hydra train or train. What's the difference here? Hydra train or train. And then we go call main. Distributed utils call main. So we now have to find that manually. So it's gonna be kind of hard because both I can't run it plus VS Code is glitching. So let's just open up the paper and let's go and see what are the main insights from this new paper. JICE and JICE Chat. Arabic-centric foundation instruction-tuned open generative large language models. Cerebras systems. Folks from Cerebras actually sent me an email before this came out that this is going to came out a couple of days ago actually. So we introduce JICE and JICE Chat, new state-of-the-art Arabic-centric foundation instruction-tuned open LLMs based on GPT-3 decoder only, and are pre-trained on a mixture of Arabic and English, including source code in various programming languages. With 13 billion, they demonstrate better knowledge and reasoning capabilities in Arabic than any existing open Arabic and multilingual models by a sizable margin based on extensive evaluation. Okay, moreover, the models are competitive in English compared to English-centric open models of similar size, despite being trained on much less English data. Interesting. I am suspicious. We provide a detailed description of the training, the tuning, the safety alignment, and the evaluation, and we release the two open versions of the model. The foundation JICE model. How does one pronounce this? And an instruction-tuned JICE maybe. JICE Chat variant, with the aim of promoting research on Arabic LLMs. Interesting. Introduction. Let's see whether there is any multilingual specific introduction. Otherwise, we can ignore the BS of usual introductions. Primarily trained on English, such even Falcon was trained on English mostly. Okay, over 400 million speakers. Okay, it's easy to find up to 2 trillion tokens for English, but for Arabic, significantly smaller. We have collected the largest Arabic corpora to date, consisting of 72 billion tokens. Still not sufficiently large for the purposes of training an Arabic LLM capable of demonstrating emergent capabilities. To address this, we train bilingual models by augmenting the limited Arabic pre-training data with abundant English pre-training data. Okay, and we pre-train JICE on 395 billion tokens, including 72 billion Arabic tokens, which we repeat 1.6 times to obtain an effective of 116 billion Arabic tokens, 232 English tokens, and the remainder being, okay, programming languages. They have designed a specialized Arabic text processing pipeline that includes thorough data filtering and cleaning to produce high-quality Arabic data. Unlike previous massively multilingual LLMs such as Bloom, they do not include anything other than Arabic and English. Neither do we relegate Arabic to a minority in the pre-training. What does relegate mean? Relegate, assign an inferior rank to a minority in the pre-trained dataset. Instead, Arabic constitutes 33%. Okay. They use a Levy, sweet glue, maximum update parameterization, custom build tokenizer, and they also instruction tune it. Yes, paper reading. Maybe worth mentioning in the Discord, we're doing a paper reading group. Where is the general channel? Why do I not see a general channel? Okay. They further fine-tuned it with safety-oriented instructions. In our deploy system, which provides an interactive interface, we add extra guidelines. Let's see how this looks like. Arabic GPT AI. Okay, I have to sign in. If anybody wants to play while we're going through the paper, let me know if you sign in and do something cool. Okay, example is shown in figure 1, so we can see it there as well. And they evaluate the model across various benchmarks. Superior in Arabic compared to all of the other models of similar size, while being competitive at English. Let's see how that translates in the real world. Releasing 2 models on Hugging Face. What's the license? I'm curious. By making our models publicly available, we hope to enable further research and development. Okay, that's just marketing speech. Let's go. Let's see what's the license. Apache 2. Oh my god, nice. Nice. Awesome work. We can maybe use this to... We might be able to use a model like this to help us boost the performance of NLLB across our Arabic languages. Nice. Nice. Awesome. Okay, pre-training data. They pre-train on hundreds of billions of words of diverse text from a variety of sources. Okay, Llama and Falcon are predominantly trained on a single language, English. While these models exhibit impressive linguistic and reasoning capabilities, their abilities do not extend, which we demonstrate experimentally below. Arabic token count 55 billion across various different Arabic tweets. Oscar, Wikipedia, English to Arabic, Maktabah C4, Ara News. This is 3-letter code for Arabic, FYI. Okay. Largest data set in the world so far for Arabic. I am curious if Arabic is one of the most spoken languages in the world. It's one of the UN languages, right? I'm curious, what would be the max number of tokens we could find, for example, Serbian or whatnot. Guys, give me just a second. Let me open the door for my girlfriend. Otherwise, I'm gonna be in trouble. Okay, I'm back. Okay, well, extending with English data and some programming language. The pre-training mix is 1 to 2 to 0.4 for Arabic, English, and code. We arrived at this ratio through extensive experiments on smaller models. We base this mix on all of the available Arabic data. I really want to start noting down these papers in our document. Just okay. Let's continue. We collect the Arabic training data from multiple sources, including web pages, wiki articles, news, books, blah, blah, blah. We also translate English content to Arabic using an in-house machine translation system. Interesting. That's why I really want to push for a very high quality translation system. Interesting. Our in-house translation system is a standard transformer sequence to sequence implemented in the PairSec library and trained on public datasets available in Opus. The English to Arabic translation performance is 31 and 40 blue points on Flores 101 and on a held out test dataset respectively. Interesting. We restrict this to high quality English resources such as English Wikipedia and books. And we apply checks to avoid translating English sources with embedded code or text that is not well structured. A breakdown of the English dataset, except the translated content, is detailed in the table we've seen above. We use text from following sources: Abu El Khair, a collection of more than 5 million news articles collected from 10 major news sources of Arabic countries over a period of 14 years. Arabic News Corpus, an open source Arabic collection prepared by Beijing Academy of AI that includes Arabic text corpora. Interesting. A clean version of the common crawl using the cleaning and the filtering described there. We use Arabic subset of the corpus. Wikipedia written in Arabic. And in-house news crawl at inception of various Arabic news channels. Okay, books. A combined dataset of multiple smaller corpora, including poetry, news, entertainment. Okay. We further augment the Arabic data by translating 3 billion tokens and 15 billion from books. We increase from 55 to 72. Subsequently, we have sampled this 1.6 times. Interesting. For English, we use the pile. Nice. From which we randomly sampled with 232 billion. And then some data from GitHub. Subset. Shows about details about the English data we use. We use the text from the following sources, part of the file. Okay. This is just file. Okay. Pre-processing pipeline. Hi, Rafael. That's a lot of data. Well, it's not, I mean, compared to what English language models are using, not really. Pre-processing. Filtering, normalizing, cleaning has shown to be a vital step in training. Several pre-processing steps combined with modules targeted at getting high quality Arabic content to generate the 72 billion tokens. Let's see what they do. An outline of the pipeline is provided in figure 2 below. We're going to see it in a second. And as explained above, the raw text is primarily sourced from publicly available datasets, as well as through in-house scraping and translation. Given that some of these sources have already been pre-processed or tokenized for NLP applications, it is essential to standardize our input. We thus subject all sources to initial detokenization step, which leaves non-tokenized input unchanged to achieve consistency. A document at this step is one article / web page, depending on the source. Wait, some of these sources have been already tokenized. Why? And with which tokenizer? How do you know which tokenizer? Yeah, compared to English, it's still little, but seems way more than the model I've seen before. Says SQ in the chat. Okay, we then apply a large number of filtering rules in order to eliminate documents that are noisy or low quality. This includes removing extremely short or long documents, or again, that's just length filtering, the same thing we're using for machine translation, or those that do not include a sufficiently high proportion of Arabic characters or sentences, which could be indicators of a document in a different language where Arabic characters appear only incidentally. Okay, they also have some heuristics there. Once a document has passed the filtering step, it is subject to cleaning and normalization. We remove non-printable Unicode characters and rare diacritic marks and normalize the text using the Camel toolset for Arabic. We remove embedded JavaScript and HTML, common source of noise, and highly frequent words and phrases, which are typically boilerplate text such as news channel name. We normalize the Arabic punctuation marks and use a lightweight NLLB LLM to further identify and remove the noisy ngrams. Finally, we apply a fuzzy deduplication step using standard locality sans LSH. After this dedupe step, the size of the English dataset was about 20% of the original. Was this processing done only on English or also on Arabic? Okay, so here's the web. Some of that has been scraped. Some is just open, publicly available, open source, and some is translated. Then they get the raw data, they detokenize, and then they have a bunch of filters, number of words, all words, characters, Arabic sentences, special symbols, blah, blah, blah. You can see the diagram yourself. Then they do deduplication, and then they have the cleaned data. What is this NLP ENGG, white, and then HPC? What does this stand for? Anyone? NLP, let's see whether Google gives us anything. Looks like the tokenization corresponds to data translated from English or Arabic. Not sure. Which is outputted as tokens in Arabic language. Could be, but why do they not say then translation goes to the tokenization? Then the diagram is weird, I don't know. And this was for English, by the way, apparently. Then they say here, things were more challenging for Arabic. Unlike English, where several large-scale and open access datasets already exist, for Arabic, this pipeline had to be custom built. They didn't filter as aggressively as for English. No worries. It is a reasonable hypothesis. And maybe, by the way, maybe tokenization doesn't mean like they're not converting them into IDs, just like chunking the words across spaces or something. I don't know. Mixing Arabic and English data. Citing chinchilla scaling laws. Optimal balance 20 tokens per parameter. This is why for English, the largest open source LLMs until recently had about 30 billion, have only 1.2 trillion tokens. Llama 2 was trained on 2 trillion. If we applied the chinchilla, we would optimally be able to train a model of 6.27 billion parameters. We could probably train a slightly larger model, as Arabic involves I don't know how to pronounce this word. Stultifization of conjunctions and pronouns. And his house is one word in Arabic, but 3 words in English. And thus the scaling law might differ a bit. Indeed, some of our experiments suggest that one might need as few as 14 tokens per parameter for Arabic, yet this does not fundamentally change the fact that we do not have enough data to train a 13 billion parameter Arabic model, let alone a 30 billion one. One possible solution is to obtain more data by adding more Arabic social media posts, but these are generally noisy. Another option is to train on mixed Arabic and English training data, and thus compensate for the missing Arabic tokens with English ones. Okay, in the future we plan to try incorporating a higher proportion of English, but we also need to be careful. For example, Bloom experiments indicate that adding 10 times as much English data results in degradation of the model performance. Okay, let's see the architecture. They use a number of improvements. Let's see the tokenizer details. Choice of tokenizer can have a significant impact. How words are split is influenced by the composition of the corpora used to train the tokenizer. A common tokenizer used in LLMs is GPT-2 tokenizer, which is also used by OPT project and GPT-3. However, because GPT-2 tokenizer is primarily trained on English corpora, common Arabic words such as EC, Y are over-segmented into individual characters. This over-segmentation lowers the performance of the model because obviously you will have to handle a sentence, you'll need bigger context length, and then the bigger the sequence, the harder it is for model to reason over it. Fairly obvious. This over-segmentation lowers the performance and increases the computational costs compared to using a custom tokenizer that is specifically designed for the target language. Okay. In order to achieve this, they trained a subword tokenizer on a combined corpus using BPE. They prepared a training corpus of 10 billion words, equal proportions of English and Arabic. Table 4 shows fertility scores against the tokenizers of PERT Arabic, Bloom, and GPT-2 on English, Arabic, and code validation datasets. We can observe that the fertility score for the JICE tokenizer is close to 1, even though the vocab has only 84,000 entries compared to Bloom, which has 2,250. Same as NLLB, by the way. That's the same number, roughly. The result shows the optimality of our custom-made tokenizer over our test corpus as compared to other tokenizers. Let's quickly see table 4. Okay, I guess this means that fertility score is probably just a ratio between the length once the sentence is tokenized, like comparison between Arabic and English or something like that. Not 100% sure. Then if that was the case, then we would have one here somewhere. Anybody knows what's a fertility score? I kind of have an intuition that this is the right explanation, but not 100% sure. Anyhow, let's see quickly. Means that the tokenizer's vocab contains every single word in the text. Okay, so it kind of quantifies the number of unknown tokens, the UNKs, the UNK tokens probably. As it says here, a minimum fertility of 1 means that the tokenizer's vocab contains every single word in the text. Average number of subwords produced per tokenized word. It says here the exact sentence. First, the subword fertility measures the average number of subwords produced per tokenized word. Okay. Then they use Alibi. We can skip all of that. Spigloo, MPU. Okay, standard stuff. Table 5 shows the number of layers, head, and dimensionality for JICE. I feel so bad pronouncing this name. Yeah, probably. Sergey has a very intuitive explanation. Table 5 shows the number of layers, heads, and dimensionality, along with the optimization, hyperparameters, values, and peak. While training, we sample the source from the source list described in section 2 and generated instances with a complete length of 2048 tokens. When the document was smaller, we concatenated several documents into one sequence. End of text is used to demarcate the end. Given the language model, the information necessary to infer that tokens separated by end of text are unrelated. Fair enough. 40 layers, 40 heads. Okay. We train using AdamW. We scale the gradient norms. They use a global batch size, almost 2,000 sequences. We base on a roughly 40 million parameter model. The model depth is 24. Okay, that's just MPU stuff. Why it's slower is better? Well, because you want your tokenizer to be concise, right? Not verbose. If you're splitting words into too many tokens, then imagine how much of a context length your transformer would need, right? You do want to be concise, yet you want to cover you don't want to have unknown tokens. You want to minimize the number of unknown tokens. Okay, learnings and observations. They conducted a series of preliminary experiments. We further sampled the English. They always train for one epoch. We experimented on models of 590 under a few data ratios. The trends are shown in figure 3. We can see that for small models, adding English impacts the cross-entropy loss in Arabic adversarially. However, this trend reverses for larger models, where adding English improves the Arabic performance. Interesting, that's very interesting. In particular, we observed that the 13 billion model trained on 1:2 Arabic-English mix outperforms the 30B Arabic only by a sizable margin. Interesting. Training infra. All training were executed on the Condor Galaxy AI computer from Cerebras, built in partnership with G42. This is a rare paper where I see non-NVIDIA GPU compute. The last one I've seen was the famous one that basically promised a new architecture that is potentially more promising than Transformer. I can't remember the name. The RedNet was, I think, was the name. So they trained on 16 CS2 systems. Sorry. Within CG1. That's a Cerebras vapor scale cluster composed of Cerebras CS2 systems. The foundation of the CG1 cluster is a engine purpose-built for max coordinates a broadcast, giving, and it receives and aggregates the independent weight gradients coming from the CS2 systems during backprop. At the end of each iteration, the aggregated gradients are sent to memory X. The CG1 hardware and software stack enables training extremely large models using data parallelism by relying on a special execution mode available within the cluster called weight streaming. Weight streaming fully bypasses the complexity of 3D parallelism on traditional GPU clusters and provides simpler and higher performance scaling. Interesting. I would love to hear whether they had any issues, instabilities or whatnot on Cerebras systems. Instruction tuning. LLMs can produce coherent text, blah, blah, blah. we include a wide range of datasets covering various domains in single and multi-turn chat formats. 10 million prompt response pairs in total, made up of 4 million in Arabic and 6 million. Where did they find those? Where did they find the Arabic ones? Okay, let's see for the explanation is probably here. Let's see the explanation. Supernatural instructions, 76 types of tasks. Okay. Okay, so then they use just a ton of these standard data sets: alpaca, chain of thought, self-instruct. Okay. Okay, just a ton of different sources. Nothing is super insightful there at the first glance. We further created our own set of question and answer pairs related to the UAE and the local region based on information from relevant Wikipedia pages and other sources. We refer to this dataset as native QA. Safety QA. Okay, and then for Arabic, we translated some of the above English instruction tuning datasets to Arabic using the same machine translation system that we use for the training data. Okay. They just prepared mostly translated English ones, but then they also prepared these native and safety QA directly in Arabic. In instruction tuning, each instance comprises a pair of a prompt and its corresponding response. Similarly to alpaca, we mask the loss of the prompt. We perform backprop on the answer tokens only, which ensures that short responses are not penalized. Interesting. Evaluations. Let's quickly skim and see what else we have in the paper. Let's skim through the tables before we decide what to read. Okay, Bloom actually performs fairly nicely. On Arabic open-ended questions. Okay, safety, related work, conclusion, out of scope use, acknowledgements, and references. Let's skim through the conclusion. We have introduced a new state-of-the-art Arabic-English bilingual model. Empowering local players with sovereign and private deployment options, and nurturing a vibrant ecosystem of applications innovation. This work supports a broader strategic initiative of digital and AI transformation to usher in an open, more linguistically inclusive, and culturally aware era. Interesting. Okay, let's skim through the appendix. Zero shot eval chat. I don't speak Arabic, so this will not be super useful. And then examples. Write a rap song about camels. I'll check it out. Let me just see this one. Listen up, yo, it's time to drop some beats. This ain't gonna be no ordinary rapping, trust. We're talking camels, the noble beasts, strong, smart, and sturdy beyond belief. They roamed the Sahara, they conquered the sand. Without them, what would nomads do? Desert expeditions couldn't take off. Hungry travelers wouldn't find food. Noblemen wouldn't cross the barren expanse. Lost souls wouldn't reach safety. So listen close, cause this verse will shake ya. Majestic creatures, strong and true, marching steadfastly towards the blue horizon, enduring heat, dust storms, and scorching sun rays, getting water from mud holes, rivers, lakes, or wells, distributing goods, carrying burdensome loads. With patience and fortitude, they face harsh conditions. You show us how to live despite adversity. Now let's celebrate you, the king of the dunes, the pillar of the desert, the friend of man. Wow, this is a very nice song, man. Amazing. Okay, just a ton of examples. You're Elon Musk. Explain why is it hard to support a human colony on Mars? Elon Musk. model card. Apache 2. Okay, we've seen all of that already. Anything interesting? Okay. So you said page 17, table 9. Okay. You know if misinformation bias being lower or higher is good. I'm confused why their larger models have higher bias. I'm not sure how they measure misinformation/bias, but I think it's actually a well-known phenomenon. Well, no, I've seen contradictory results. I think GPT-3 was like bigger models were actually more truthful. So I don't know. I'm not sure really. Let's just quickly skim through evaluation. And then I think we can ignore the safety part and yeah. Let's just skim evaluation, we're done. Just curious to hear a bit more about what they've done. Why are you reading all these papers live? That's a good question. I don't know. My whole YouTube channel was about paper reading, so mostly. People love reading papers, especially when they don't have enough context. Like it helps. Some comments I can make can help people understand better stuff. And also because this paper is relevant to our work on NLLB, so as we can potentially leverage this model for translating, getting more English text. Sorry, more Arabic text. Okay. For each language, our eval encompasses aspects such as knowledge, reasoning, misinformation, and bias, blah, blah, blah. And additionally, they hired native speakers of Arabic to manually translate the MLLU from English to Arabic. Interesting. World knowledge. Okay. Common sense reasoning. Details about the Arabic, misinformation and bias, evaluation setup. They compare with 20 baseline models that support Arabic and or English. We adopt the LM evaluation harness framework from Eleuther AI. We went through this one a couple of days ago, actually. To evaluate each model in a zero-shot setting. Okay. Table 9 shows some results. Average result across these domains. Best baseline model for Arabic is Bloom Z. Falcon lags behind. Okay. And results for English given in table 10. Interesting. We can further see that Chat 13 billion performs on pair with the recently released Llama 2 Chat 13 billion model, even though the latter was trained on 2 trillion of English word tokens, while our model has only seen 232 English word tokens. Wait, how do they evaluate that exactly? Also outperforms other baselines. Okay, let's see table 10 for English. Wait, these results are too good. How can Llama 13B be as good as this model with 13B? Highly suspicious of the results here. Again, they've manually translated some of the instruction datasets, Vicuna instructions 80. Okay. GPT-4 evaluation results. Okay, guys. What are the interesting takeaways here? I guess it's always about data. Honestly, over the last couple of years, it's only about data. I find it interesting to see how this effort looked like when it came to collection of data, how they used translation of 16 billion tokens from English to Arabic. That was super fun. And then upsampling to 1.6 and then mixing that with English and figuring out that for larger models, once you get to like 7B or 13B, English helps. Whereas for smaller checkpoints, apparently it was like causing some catastrophic forgetting for Arabic. So it was more interfering than helping. So those are some insights that were interesting to me personally. Also the Cerebrus system that was used for training. I would love to see a bit more like logs, if you know what I mean. Something similar to like OPT logbooks, just to see whether they struggled and how it compares to NVIDIA GPUs, the experience in general. Those are some thoughts on the paper. Let me see whether something else standed out for me. They had in-house translation teams as well to manually translate some of the texts and datasets like MMLU. That was also fun. They used MPU to find the optimal hyperparameters for a smaller checkpoint, and then they just used the MPU laws to just scale up hyperparams to bigger checkpoints. That was also interesting. Any other thoughts, guys? What else? Surprising evaluation results. I'm not exactly sure how they achieve same results as Llama checkpoints on English. This is weird. How can Llama be almost just a bit better than this model for English? Sus results, yeah. Cool, guys. Oh, LinkedIn, no, no, man. Go to Twitter. Just find people who are experts in machine learning. Most of those folks are just on Twitter. LinkedIn, I don't use LinkedIn to find papers. I am the person who shares papers on LinkedIn, so I guess people see it from me there, but in general, okay, we are done there. Let's see what else we have. I'm still waiting for this to complete. The filtering pipeline is super slow. Oh yeah, MPU is super cool, Rafael. You should check it out. Greg Yang, actually the main author of that line of papers, is one of the founding engineers behind XAI, Elon Musk's recent company. I have 3 friends who are in that company. I worked with a couple of them. Igor Babushkin was also at DeepMind. He was at OpenAI and then at DeepMind again. Toby Poland. I collaborated a bit with him back at DeepMind. Okay. We read the paper, analyzed the training script, and then, yeah, we're kind of blocked now by the filtering stage. A cool thing would be if we could kick off a training run with some dummy data. I might have some old, let's see. I might have some old outputs from before that we could use to run this. Let's see, just give me a second. Let's go to Stopes. And then prepare data. Prepare data, and then I might have some data here under data bin. No, here I don't have any. Okay, here we have some data that we can use to just kick off the training runs so we can debug it. And here as well. Okay, let's try and use this. This is English to Spanish. So I think we can use this to run the training runs. Let me find the config file for training. Just a second. So copy this path. Open up Fairsec. Yes, they are. Check it out on Hugging Face. As far as I saw, they are Apache 2, which means you can freely use them for whatever you want, even commercial use cases. And they're all freely available on Hugging Face, as far as I saw in the paper. Train, dense, and then where is the data specified? Dataset FBC chat. And here, okay, here you can see we are using precisely this. Okay, so I think I actually have, let me see, I think I might have the exact instructions, settings to run the train script. Let me check JSON. Okay, here it is. Here are some of the settings I previously used. Fine-tune direct train. I think we can use this one. fine tune, generate, interactive. Okay, let's use this direct train to kick off the run. Data bin. Okay. Direct train. Let's open up the sweep, this one, and let's just trigger the correct one. So we need direct train, and let me hit run here. Let's see whether this will actually work. Nice, nice, nice. Oh no, there is an error apparently. Okay, I do have an error here. Maybe I have to run the train directly from Fair6 CLI. Let's try and run this one. Okay. Okay, guys, this might be the right. Yes, nice. This looks like this is the right method. Let's run this. I'm not sure why my linter is glitching. But we'll be able to run. Let's just see what's distributed main. Here it is. Hit F5. And here we are. Let's quickly understand the code path that we'll be going through once we prepare the data. We'll have two processes because I have two GPUs. Let me close down this one so we can easily see what's going on. Let me just close this. We can ignore these distributed details and just focus on the logic in the main function. Okay, initialized, and then here's the main, and here it is. Fair6 CLI train.py main. Set up the task. Let me see whether I can fix the linting because this is terrible to watch. I'm gonna hit this. Just try and exit. Close this down. Open up another window. Open recent. Okay. Is this better? Finally. Linting died for some reason, so let's now kick it off again. Main. Let's go. I can hit F5 until we get to the main. Hit F5, hit F5. Here we are. Okay, just setting the torch seed for reproducibility. Verify that where is the checkpoint going to be? Okay, fairsac model checkpoint, save the directory. Verify this exists. Set up the task, and the task is going to be which one? Let me just print config task. Okay. There is a ton of variables inside there. Not really easy to parse that. Let's maybe step into it. Let's step into the task, setup task. Task name, translation multi-simple epoch. So we grab the actual task from the dictionary, and that one is translation multi-simple epoch task. Okay, intuitive enough. And then we run setup task. Prepare. Again, keep in mind this is fairsac. They use the same code path to run every single one of their trainings. Although to the best of my knowledge, they do have internal version of fairsac. Load languages. We load all 202 BCP47 codes, and then we check if training, which should be set to true, then split. Load dictionaries. Let's step into this. Extra lang pairs, none. Source langs, English. Target is going to be Spanish, as we saw before. Spanish, Latin. Then we split the paths here, and because we only have a single shard, we just end up with a list that has a single shard. Later, once our actual filtering is done, we'll have many more shards. Okay. So if the source dictionary exists, is none, then we'll load for English Latin. Let's see what we do there. We format using this language, and then path 0. So we end up with a dictionary. Okay, we actually loaded already. So load dictionary just loads from this particular path. And we can see that, let me show you in Stopes. We open up Stopes. If I show you the binarized data here, so it's pulling the dictionaries from here. Here is one. That's the English one, and here is the Spanish one. They're kind of dummy dictionaries. I just played with it a bit. So it's not really properly trained, but it's good enough for the purpose of just understanding the code. Okay. Just some error checking. And then we'll load dictionary for target as well, which is Spanish. And we return back the dictionaries, as well as the language list, as well as the training flag. Okay. And that's it. Now we are in the init method of the translation multi-simple epoch task. That was just the preparation phase. Now we're actually in the init function. We grab the source languages, which is English, and target, which is Spanish. We check the dictionaries. What does this do? Okay, we grab the source dictionary and we grab the target, and then we assert that the source equals to this one. Okay, just some basic error checking. Build a sampler. Sampling method. Okay. Set up data manager. Language pairs, languages, dictionaries, sampling method. What's the data manager? Get language IDX. What does this do? Get the language token, and then just retrieve back the language indexes. Okay, just trying to get some understanding of the code base. Obviously much better to just run, and then once you hit issues, debug stuff, but also I love to internalize the code bases before I start running them. Okay, so we wrap the model. So here we build the model. So now we're just hitting the second process. Let me see. Let's quickly get to the stage where we were before, and that's here. Let's disable breakpoints except for this one. And let's now step over it. So the interesting part will be the build model. Enter the build model. Here we build the model, and then we do some quantization potentially. So let's enter the build model function. Model type is a transformer. And then given that model type, we extract the actual class, transformer model, and then here we actually pass the config, and this is where the model is going to be built or not. Wait, what does this do? Let me step into this. just a ton of, this just sets up the arguments for the transformer, and then the actual build function is here. So first the base architecture. Okay, we've gone through that same function just before. Encoder layers to keep, decoder layers to keep, nothing there. We skip over all of that. We grab the dictionaries for the source and the target. Share all embeddings. I guess that means share the input and output. We grab the config and then build model. Build the embedding, embedding dimension, embedding path, source dictionary. Yeah, Twitter is not 1 week earlier, but I don't know. Twitter is real time. LinkedIn is batch. LinkedIn has a ton of people who have never done any serious machine learning, and they're trying to position themselves as experts, which is weird. Although Twitter has the same issue. The thread boys. Build embeddings. Okay, you gotta hate these big frameworks if you try and actually step. I'm not sure how is anybody, like how many people have this code base internalized? That's my question. How many people in this world actually understand details behind, have parsec internalized in their minds? Transformer model, build embedding, and then you call the super class and you called its build embedding function. It's just turtle after turtle. Number of embeddings 50,206, embedding index. We build the embedding class, which is gonna be hopefully torch at the end. Let's see, let's enter here. We grab that random generator state. Device CUDA or not, why not? Because this is set to false, okay. Okay, and then we just build torch empty. And then we initialize it using normal distribution, constant here, 0. And we call the NN embedding. So this is parsec models transformer base embedding. Finally. And if path is provided. Okay, that's building the embedding. And then build encoder, build decoder. I won't get into those. And then call the class, the base one. Quantization, retrieve back the model, wrap it up into FSTP wrap, just fully sharded logic, and then build criterion, which is going to be what here, cross entropy, label smoothed cross entropy. some logging. Skip over all of this. Skip. We'll load the data set, the validation data set. We build the trainer, which stores the config, the task. The criterion, the model, everything. This should be false because we're not using pipeline parallelism. Okay. And then that kicks off this guy, the second process. Let's just put a breakpoint here, hit F5. Let's get to the trainer. Enter here. Go all the way down to where we stopped. Somewhere here. Hit F5. Okay, here it is. Now we can continue with both processes. And then that's it. So that's the trainer class. Super complex. Some logging. Load the checkpoint. We don't have any checkpoints, so none. Trainer. Let's see what happens if none is set. Do we just ignore, or because we already loaded, I guess, random weights by just constructing the transformer? Let's see. Anything interesting here? Suffix shard1, checkpoint path, model checkpoints, save directory checkpoint, last shard1, pairsec. Model checkpoint. Here it is. Save. Save directory. There is nothing in there. So that means this is going to be first launch, true. And if it's the first launch, we just skip over all of this. Load checkpoint. Checkpoint path, reset false, optimizer overrides empty. Let's just enter into the load checkpoints. F11 is distributed true because we have two GPUs, so we are basically doing data parallelism in this run. Okay, nothing happened there, so it literally skipped over everything and just retrieved back none. Get the train iterator. So I find it extremely unintuitive that inside of a checkpoint utils, you have a load checkpoint function, and inside that function, you're retrieving back the train iterator. What does that have to do with model checkpoint? Nothing. Same with learning rate step here. I guess that's the reason they're creating Versec 2.0. Okay, we are up in the main function, and here is the actual train logic. So this is where the main algorithm happens, and then we just change the learning rate, and we get the new training iterator, which is also not intuitive. Why would you have to get a new iterator? Why not just loop through it? And that's it, that's the main function. We now iterate until either learning rate is smaller than the stop minimum learning rate, which is 1 nano, or if this function returns should stop, then we break out of the loop. Otherwise, we just keep on looping. Should stop will probably retrieve false once we hit the number of steps or epochs that we set. And then we just do this. Is this supposed to save the checkpoints internally? Who knows? This is Versec. Everything is possible. Okay, rant over. Let's go into train. Okay, again, we are kicking off this second process. Let's just get all the way to train. Hit F5. Enter. Okay, snap. I accidentally, let me just go back here. Let's disable all breakpoints except for this one, and let's rerun. No, I want to kill this one. Just kill it. And now rerun the whole thing. Let's see. Okay. Let's put a breakpoint here and let's hit F5. Grab the next iterator, counting iterator. Wrap everything inside of a progress bar. And then grab the samples. Samples has our data, both the target and the source. Samples, let's see what's the keys behind this one. Samples ID, number of sentences, number of tokens, network input, and target. What are IDs? Okay, these are probably just the IDs of these 5 sentences. And then net input and target are actually the tokens for the transformer. So net input consists of source tokens, source lengths, and previous output tokens. Interesting. Train step. Okay, this is where the main logic happens. Let's enter. Train step. Set model and criterion to train. 0 degrees. And then we go to the samples. We prepare the samples. This is just going to convert to FP16 and push to CUDA. And finally the train step. So again, look at this stack from main to inner to train to inner to train step. It's always like this. You start generating abstractions thinking you're going to improve stuff, and then you end up with a mess. Okay, we're profiling and then potentially doing the mixed precision, but here, because this is going to be set to false, enable this false, so this will not be activated. And then criterion, model and sample, we just run. So this is, I guess, the forward pass as denoted here. Let's do F11. Here is the forward pass. We basically extract the net input, which is the dictionary. Let's enter here inside of the model. We are deep in the FAIRSec code base. Okay, we are inside of the actually fully sharded data parallel. We are now in fair scale. Let's try and get to the actual transformer. Okay, here we are. Snap. It is stuck for some reason. It could be that I have to go and unblock the second process. Yes. Let's just go all the way to here. Enter the train step. Let's go all the way to this one. And then criterion. Enter here. Enter here. Okay. Okay, we are back. Snap, we passed. Oh my god, we passed by one line. Let's try, let me grab the second process. Let me grab the second one. And let's enter the module. No, where are we? Okay. Here we are. We are inside of fair scale again, calling module. And we are finally in the transformer. This is the forward pass of the transformer model. Oh my god, look at this stack here to get to the forward pass. Crazy. Encoder, decoder. So here are the source tokens. It's just a tensor. I guess 20, 48. No, 366. Why is this? Okay, these are just some dumb examples. So I won't give too much attention to the actual numbers. And okay, 66, 66, 65 are the token lengths. Return all hiddens, true. Let's enter here. Forward scriptable. Okay. We ask where is the padding token to create the padding mask. And then if the type is XLA, or if there is any padding, then we set this to true. And then forward embedding. Transformer encoder base. Embed tokens. Okay, and we just call we're now in Torch embedding module, we just call the embedding. And then we are back with 366 something, 366,024. We multiply that with the scale parameter, which I have no idea why it's equal to 32. Positional embeddings, dropout, and we retrieve back the values here. Okay, this is just in the actual heart of the transformer. I just wanted to see a bit how parsec implementation looks like. For me, this is not particularly informative. Maybe for some of you it is. Do you guys find this actually useful? And then we return back this, the padding, the embeddings, the states, just a huge dictionary. And then we also append some of these internal states. Okay, and then we go through the layers and we just do forward pass through the layer, and we append stuff because this is set to true. Let's just exit from here, layer norm, results, and return the results. Okay, and then the same for decoder. And we are done there. Switch to main FP32 parameter shard. We maintain this invariant throughout the code. After each function, this also ensures that after the first forward, the optimizer state will be initialized with the correct D type, since optimizer state is typically initialized lazily. Register pre-backward hooks to all gather the parameters for the backward pass if output squared was needed. This won't register anything if we're in the eval mode. Okay. Free SSD upload. This is some torch stuff. Fair scale stuff. And nothing happens there. Okay. And that's the forward pass. Happens inside of the task itself. No, label smoothed cross entropy criterion forward. Let's see the shape of the output. It's actually a dictionary or a tuple. What is this type? Tuple. What's the length of it? 2. 0 is 50,206, which is the vocab size, so that makes sense. And then let's see, 1 is actually a dictionary. Okay, so that's the dictionary with inner states and everything else that we were retrieving. And now we compute the loss. Reduce, set to true. We pass in the sample because of the target. And we compute the loss negative likelihood. Sample size, so we can normalize stuff. Okay, that's it. And then we do backward. Backward. And then we just return back the loss here. Okay, and that's the main loop. Inside of the train step. Okay, I think I have to trigger the second process. Okay, here we are. We'll reduce across workers. So it's literally taking the gradients from both of my GPUs and reducing them. And then multiply the gradients. So this is why we have the sample size here. Sample size 1 handles the case of a 0 gradient. Okay. Multiply the grads. Okay, we're just going through the same code path with the second process and flipping the gradients. optimizer step. Okay, a ton of supporting code. But mildly giving me a headache. Yeah. That makes the two of us. Okay, I just wanted to roughly see how stuff looks like. This is not super useful. Okay, train step, we are done. This is just some supporting code around the main logic. So that's where our model will be training. That's the code. We now just have to finish the filtering stage and prepare the data after that. We've seen that code today as well, the sharding, the binarization, the validation, all of those steps. So that's it. Let me just wrap up this stepping through, and then let's see what we can do. We have 40-ish more minutes for the stream. We can maybe even wrap up sooner because I'm blocked by the filtering pipeline, and I want to go and just see what's going on Twitter, whether I can pick up something interesting for tomorrow, so that we can continue tomorrow. Also, my VS Code is glitching here, so I think that this might be a good moment to wrap this up. Why are you glitching so hard? Subprocess. Let's just maybe kick off the second one. I think I have to start this one and exit from here. Exit. Here we are. Validate and save. I don't think we will be running through this. Oh, we actually will. Interesting. Let me just remove the breakpoint here. Let's hit Shift F11 to exit. Shift F11. Shift F11. We're again in the core code here. Validation step had the okay. Let's exit here. We are in the uncharted territory where no man has ever debugged. Let's just exit here. This is the validate and save function. Okay, should stop. Yes, and then log progress and return stop back. Shift F11 should stop break. Both processes are exiting. We are now back in the distributed main, and here we are. Barrier. It's waiting for both processes to hit it, and then it will unblock. And we are gonna effectively end the program. Okay. That's it, guys. We've analyzed the training script. Thanks for streaming. I'm enjoying hanging out and thinking, learning. Thanks, Sergey. Appreciate the kind words. Okay. Let me just see whether I can do something else here. There is one thing I could do, and that's to double check what happened with the mined data. Let's open up the download mined data script. Let's go there, find the data directory. Examples, NLLB data, download mine. So I basically used Hugging Face to go through this, and this is the LNAI dataset, 450 gigabytes. I basically just went through the English to Serbian direction and tried to download it, and then there was some error, but I'm not sure where it downloads the data. It might be my local cache or something, but I'm not sure where exactly it downloads the data. So let's kick this off and see whether this is already loaded. F10. Okay, it's actually doing some generation of training split. Let me open up that particular repo on Hugging Face and see the files that they've implemented. This is the main logic, I guess. The pairs. What's this dummy one? Dummy data. Okay. Let's see this file. Description, homepage, CC matrix citation, LNAI URL, storage Google APIs, NLLB. That's the URL for the dataset. StatMT URL. That's something for CC matrix. Source. If the URL starts with StatMT URL. Builder configs. NLLB. Okay, what do we call here? We go through the pairs. CC matrix pairs as well. They get the mappings, and then they create the NLLB task config with the name, which is basically the source target direction. Okay. So builder configs just calls that particular function. And then there is the NLLB task config, which is basically just your simple, almost like a data class here. Okay. Translation dataset for the languages that we specified. Laser score, LID. If it's stat empty, then these are the features, and then return the dataset info. Split generators. Download and extract the URL, and then once you have the local file, then you can start doing this. So we have the local file somewhere. I'm curious where this is stored. And then we're running this split generator, which opens the file and then goes through the data, does some processing. We grab these objects and then we just yield them. That's the generate full examples. The minimum examples do what? Some smaller examples here. Go to the root of the repo and run dataset CLI. Okay. And this generate example is probably called by the split generator. This is just some API function you have to implement, just the interface. Okay, fair enough. Because this might take a while, 2 million. Let me just, my goal is just to see and understand what's going on in the behind the scenes here. Let's enter here. Let's see where this dataset is stored and how big it is. Reuse dataset if exists. Download and prepare. Okay. Let's enter here. Okay, here it is. I guess that's where the location is. Let me just save this somewhere. Get the token paths. Storage option none. Is local, true. Output directory. Download mode base path. Download config. Download manager. If it's local, grab this path, parent, make directory. File locking only with local paths. Did anybody step through the Hugging Face datasets library before? Path join. Does it exist? False. If it exists and download mode is reuse. Okay, otherwise, if it's local, preparing, download size 1994. Oh, this is not sure in which units this is, probably bytes. Post-processing size in bytes. Okay, so let's just see what's this size in bytes. We can also just directly open up the file. Oops. So this many bytes. Okay, around 1.5 to 2 gigabytes. Check manual download. Okay, this is where it started doing this thing, which is not that intuitive. Well, maybe prepare portion. Okay, let's rerun this. Hit rerun. F5. Okay, let's see here. What happens here? Okay. Prepare the split. Builder, download and prepare. Check duplicate key. Duplicate key is true. File format arrow. Whether anyone played with it, whether anyone stepped through the actual code behind the implementation, not just used it. Are you familiar with the design of the library, stuff like that? Okay. Let me just go here. Builder lock incomplete. Okay, this is just some Hugging Face specific stuff. So it did not download the data, or did it? Prepare split single. generate examples. Okay, generate minimal examples. Okay, we are now in the actual function we were looking, right? This is the function we were looking at before. So deep within datasets, they have this function, generate examples, and then this is implemented here. So if the source is stat empty, it goes through this function. Okay. So let's see where that generator is triggered. Probably somewhere here. If we get to that line. Writer class, hit F5. Okay. Here is the generator. Okay, so we open up a file path. Let me see. Okay. Huh, interesting. Okay, one of them has 4.3 gigabytes. This 19A has 4.3 gigabytes. So that means it has been downloaded. So we just open it up and then go through the examples. And here it is. Nice. So we have the sentence from the dataset, which is some number, which is probably something like LID score. And then tab, your enemy has to be poverty. And then Serbian sentence after the tab with some weird quotation marks. Vaš neprijatelj mora da bude siromaštvo, which is the correct translation. Interesting. So we do right stripping of the new line character and then splitting on, so we have score, source, and target, and that's what we're gonna yield. Okay, and then we encode that example. Interesting. So I'm curious, how can we just download this data without having to use Hugging Face necessarily? So I just want to have it downloaded same as all of our public primary. That's why I'm analyzing this. I'm just trying to, well, I'm also just curious partially, but I also want to understand how we can just grab the directories with data and then shoehorn them into the desired structure that we already have for our primary data set. Features. Okay, so we now process the features, encode examples, and then we write using the writer. Okay, this is finally the filtering pipeline. Okay, let's enter here. encode examples. Cast to Python object. Encode nested example. Okay, nothing super special happened. And then we write somewhere. I'm just curious to see where do we write this. Okay, I didn't see that. Where did we write it? So we just append it to the current examples. So there is no saving along the way to the file system. And then again. And then okay. So let us put a conditional breakpoint here to say when we hit it 10,000 times, please trigger it. Can I somehow grab the path of this one? Copy the call stack. Let's see what's that gonna do. Okay. Let me just copy the call stack. Let me hit F5. Remove this. Hit F5. So we're gonna hit that particular breakpoint after 10,000 steps. This might take a while. That's why I was let me see what's going on. How many examples do we have? Why is it 1? When do you write? And where do you write? So at the end, we close the writer, and that's probably going to flush the leftover data. And then we just yield total number of examples. Okay. Let's leave this to run as well as the filtering pipeline, and then we can continue tomorrow in the morning. Until then, we'll have some results. Cool, guys. Long day. 10 hours of streaming again. let's continue tomorrow. See you, enjoy your evening / day, wherever you are, and see you tomorrow. Again, for those of you who don't know, check out the channel that we use to collaborate, which is basically this channel, the Meta NLLB replication channel in my Discord server. That's where we're gonna be posting all of the updates and everything related to the project. So go there and see you tomorrow. Take care, Brian. Take care, SQ. See you guys. Cheers. See you tomorrow, Sergey. Bye-bye.